Good morning to everyone. Today I am presentation about system of second order linear elasticity in PDA. And myself K. Vijay Kumar, branch mechanical engineering, semester 2. Introduction to semester of system of second order linear elasticity in PDA. The system of second order linear elasticity in PDE describes the behavior of decomfortable bodies under the roots. Related to the measure parameters 1 by O square by d square by over dt plus d and dy by dt. Kx is equal to y and it is governed by a set of partial differential equations that relate stress, strain, pain and displacement. These equations are derived from the law of principal quantum mechanics and Hooke's law, where W1 equal to natural frequency and gamma is equal to damping ratio, K is equal to 1 by K and 1 by spring constant, M equal to d square y by dt square plus lambda dy by dt plus ky is equal to f by t is equal to m d square by t equal to dt square plus long lambda dy by dt and y is equal to 1 by k of ft. Background of linear elasticity equations. The linear elasticity equations are a set of PEDEs and they govern the deformation of elastic materials. Use the geometric equations for linear elasticity. E zx equal to 1 by 1 by z. Dou u by dou z plus dou w by dou x. And EZY is equal to half dou v by dou z plus dou w by dou y. And EXY is equal to half dou u by dou y plus dou v by dou x. These equations are based on the assumption that the material's response is linearly related to applied loads. And to verify the following complementarity equations, to the dou u by ex by dou ex plus ey. These equations are based on the assumption that the material deformation of linearly related to applied loads. They involve second order derivatives of displacement to the spatial coordinates and use the second order derivatives of displacement to the material response in linearly related to the applied loads and background linear elasticity equations. No components of the linear elasticity system. The system of second order linear elasticity typically includes equations for equilibrium, compatibility, and constitutive relations. Equilibrium equations ensure that forces and acting on the infest material element of materials are balanced. Compatibility equations relate the strains to the displacements in a consistent manner. To the here we show the diagram, and the order contains a second order linear elasticity. An element of the materials are balanced and displacement consistent number. Next, governing equations in linear elasticity. Governing equations are constant. Destiny follows. Cornell engineering. Conservation of mass. V dot V dash equal to 0. Dou E by dou E plus dou E by dou E plus Vc by G equal to 0. These the governing equations in linear elasticity are typically expressed as a system of second order partial difference equations. These equations involve the stress tensor and material properties such as Young modulus and Poisson ratio. The equations are often written in matrix form to capture the spatial derivatives and materials to the various of relations to the stress tensor and material properties such as Young modulus and Poisson ratio. The equations are in linear elasticity are system of second order partial differential equations to capture and write in matrix form the spatial derivatives and material properties. Next, boundary conditions in linear elasticity. Boundary conditions in linear elasticity are three partial differential equations in displacement: second order each coordinate, second order in time, second order in partial on a free surface in each direction to specify stress or displacement, but not initially conditions for direction specified displacement and velocity. Boundary conditions in linear elasticity specify the displacements or traction to the boundaries of material domain. These conditions are essential for solving the PDE system and obtaining a unique solution. Common boundary conditions include the Dirichlet boundary and condition specified displacements. Neumann boundary conditions specified and corrections. Linear elastic material are into three different parts. The second order in each coordinate, second order in time. On a surface in each direction specify stress or displacement but not both. Initial conditions for each direction specify displacement and velocity. Next, finite element method for solving linear elasticity problems. Beginner finite element method. The finite element method is a popular numerical technique for solving linear elasticity problems. It involves the districting and the domain into finite elements and approximating the solution over each element. By solving the resulting system of algebraic equations, one can obtain the displacement fields and stress in the material. And then we have to know that the algebraic equations can only obtain the displacement field and stress in the material, and we know the numerical technique for solving linear elasticity problems and into domain into finite elements and solution over each element. Applications of linear elasticity in engineering. Linear elasticity theory was hiding applications in engineering such as structural analysis, material designs, and geomechanics. We need to know the theory was wide applications in engineering such as structural analysis and material design and geomechanics. It is used to predict the behavior of structures under various loading conditions and assess their safety. Now we need to know the loading conditions and assess their safety. Finite element software packages like ANSYS, Abacus, and Cosmos utilize linear elasticity principles for engineering simulations. Linear elasticity, we know the geomechanics, and it is used to various loading conditions, assess their safety. Finite elements software packages like ANSYS and Abacus for engineering simulations. Challenges and limitations of linear elasticity. Linear elasticity, we know the challenges and limitations. Here the diagram is elasticity of a linear demand curve graph. Elasticity is larger than 1. Elasticity is smaller than 1. Demand quantity price. Here to be taken the numbers as events and normal numbers. Events are 2, 4, 6, 8, 10, 12, 14, and the numbers are 1, 2, 3, 4, 5, 6. The price is 7. Next, linear elasticity assumption may not hold for the highly deformable materials or large displacements. The systems of PDE can become computationally expensive for complex geometrics and nonlinear material behavior. Incorporating material nonlinearity, large deformations, and failure criteria require more advanced and consecutive models and numerical methods. The slope of a linear demand curve is constant, but its elasticity is not. The demand schedule is maybe in the table was that used to calculate, and we know to know the price elasticity by the midpoint method, and it is and the points were low price and high quantity. The demand curve is inelastic. Points in a high place, it is used to demand curve is elastic. Feature development in linear elasticity. Research in linear elasticity is focusing on developing more accurate consistent models for non-linear materials. Advanced computation techniques such as isogeometric analysis and meshless methods are being explored for efficient solution of PDE systems. Integration of data given approaches with linear algorithms, elasticity theory is direction for predictive and modeling for the engineering methods. Next, the last one is the conclusion. The system of second order linear elasticity in PDE provides a fundamental framework for analyzing the mechanical behavior of deformables. Here, the second order linear differential equations. Equations be like engineering examples, spring dashboard systems, and torsional motion of a weight on a twisted shaft, LRC series circuits. And we know the figure by solving the generating governing equations and applying appropriate boundaries conditions. Engineering can predict the response of structures under loading, and continued research and advancements in numerical methods will further enhance the applicability and accuracy of linear elastics in various engineering discipline methods. Here we know that they predict the response of structures under loading. The punctuality and appropriate boundary conditions may use it to the response of structure under loading and accuracy of linear elasticity in various engineering disciplines. It is used to in mechanical behavior of deformable materials. And equations be like d square y by dx dt square plus p of dy by dt plus q of t by y is equal to g of t. We know the boundary conditions. Engineers can predict the response of structures under loading. And that's all. Thank you.